Hello, warm greetings all of you. My name is Lalrod Puya from Mizoram University. Today I am going to present spectroscopic studies of Prodomine B dye and doping silica matrix. As we know that laser dyes within various hosts, that is in liquid and solid phase, suggest attractive material for using to enable laser applications because they have large fluorescence bandwidth. Also, dye laser has many advantages such as in operation, lack of toxicity, inflammability, and high photostability. And nanoparticles can also be embedded for improving the optical property. And there can also be transfer of energy between nanoparticles and rhodamine B. This transfer of energy has great interest in science and has potential application in the areas of luminescence taking, imaging, medical diagnostic, and most recently in biosensor. So that's why in our research work we study the optical properties of rhodamine B dye in liquid and solid phase that is embedded in silica host. And we study their characterization and CDS nanoparticles doped with concentration of rhodamine dye 10 to power minus 6 to 10 to power minus 3 concentration. Our investigation provide information about interaction between CDS and rhodamine. So for our experimental method, we follow the Sol-Gel method for the sample for our sample preparation. Rhodamine dye solution is prepared by mixing 20 ml of ethanol with RBH rhodamine concentration S from 10 to power minus 6 to 10 to power minus 3. For forming silica, TEOS we use TEOS as our main precursors in the presence of distilled water. And for the preparation of cadmium sulfate, we adding together cadmium acetate, mm, triethylenamine, NH4OH, thiourea, and distilled water. The spectrum that is absorption and fluorescence were recorded in UV visible region using HORIBA imaging spectrometer and synergy software. So in our result and discussion, let me go straight to our first graph, that is graph of absorption spectra of rhodamine B dope with ethanol at three different concentrations and dope with silica glass, that is what we have shown in figure number 1 and figure number A and B. Here we can see that absorption intensity increases with increasing the concentration of rhodamine B. In absorption spectra of rhodamine B in silica host, the wavelength maximum lambda max occurs at 526, 553, and 566 nanometers. So the rest shift occur. In fluorescence spectra of rhodamine at different concentration of also dope in silica glass, that is what we have shown in figure 2A and B. The band tunability for liquid phase is from 520 to 750 nanometer, and for solid phase is 450 to 800 nanometer. So we can see that solid exhibit a broader than the liquid phase. And fluorescent wavelength of dye in silica glass is slightly blue shift as the concentration of dye increases. And we can see that intensity becomes maximum at 1 is to 10 power minus 4 mole per liter and minimum at 1 is to 10 power minus 3 concentration. So for our step number experiment number 3, that is absorption and fluorescence spectra of rhodamine dye in different concentration with a fixed concentration of CDS, as we shown in figure 3 and 4. Here we can see that absorption band having a longer wavelength was found at we found out that 568 nanometer, and smaller band was found at 526 nanometer. For fluorescence spectrum, we can see that emission transitions start from vibrationally lowest lying level of first excited state S and end at vibrationally ground electronic state. From absorption spectrum, that is from the absorption graph, we can calculated the molecular absorption coefficient also. And for fluorescence spectra, wavelength increases from 592 nanometer to 593 and constant at 593 nanometer onwards. If there is change in spectroscopic properties, that is due to dipole-dipole interaction and hydrogen bonding between our samples, that is CDS and rhodamine dye. For step number 4, FRET, that is fluorescence spectra with varying concentration of rhodamine B and fixed concentration of CDS for excitation wavelength 370 and 450 as we shown in figure 5 and 6. It is observed that fluorescence spectra of CDS gradually quenches with corresponding rhodamine dye fluorescence at 592 nanometer. That is when CDS is excited. Its excitation energy is transferred to rhodamine dye acceptor through dipole-dipole interaction. They can transfer energy because of fluorescent quenching of donor molecule with increasing the fluorescent intensity of acceptor. This spectrum shows, that is figure 5 and 6. This spectrum shows a good Fred pair between them. So for our next step, that is energy transfer between CDS and rhodamine as shown in figure 7. This shows a good spectral overlap between fluorescence spectrum of our donor CDS and absorption spectrum of the acceptor rhodamine dye. So for excitation wavelength of 317, fluorescence peak of CDS for 536 nanometer and absorption spectrum of rhodamine B for 529 nanometer shows a good overlap. This spectral overlap occurs due to fluorescence quenching of donor. This confirms that there is energy transfer from CDS donor to rhodamine dye has a high probability transfer. That is what we have find out from our result and discussion. And also let me go through our conclusion. In our conclusion part, we have also mentioned some works what we have also studied. Um, Here we have also the studied molecular extinction coefficient, absorption fraction, fluorescence, cross-section, fluorescence, quantum Hill, fluorescence spectra, absorption spectra, spectrum overlap. From our graph, we find that redshift in rhodamine dye laser because wavelength increases as the rhodamine concentration increases, and the energy transfer efficiency using donor CDS and acceptor rhodamine B is 24.13% and 40.89%, and average lifetime of CDS is 2.16 nanoseconds, and with transfer energy efficiency is 8.26%. Okay, thank you.